Hello, here we talk about a rectangular loop entering into a magnetic field and then getting out of the magnetic field. And we are given five instances of the rectangular loop. So let's call this instance 1, 2, 3, 4, and 5. The magnetic field is confined within the rectangular region that is shown here in blue, and outside there is no magnetic field. So let's talk about instance 1. The induced EMF and the associated induced current depends on the change in flux. There is no flux to begin with because magnetic field is zero in this, so flux is equal to zero. If and it remains zero unless it reaches an instance 2 where it starts entering the magnetic field. Until then, there is no change in magnetic field because flux being zero does not imply that the rate of flux is zero. So we should also clarify that the rate of change of flux is also equal to zero, and that implies that the induced current and voltage is instance 2. The flux is changing because area is now the induced flux is getting contribution with that shaded region because magnetic field is there only on that boundary. So so first let's argue the direction of current. So flux is increasing, so flux is increasing. If flux is increasing, there will be an induced magnetic field inside the loop, which will be in the opposite direction of the existing B. It's in the opposite direction to the original magnetic field. If that is the case, that means B induced is coming out of the whiteboard. If B has to be coming out, then the current in the loop has to be in the clockwise, sorry, counterclockwise, right? I is counterclockwise in the loop. That means this is our loop and current is going in this direction. That leads to an induced magnetic field that's coming out of the whiteboard, which is opposite to the direction of B because the system tries to decrease the flux. What is the induced EMF, electromotive force, which is V effective, is the derivative of the flux, which is B times A, which is L times, let's say, X, which is the length down here, which is associated with how much length of the how much side of the wire is going into the loop, which is changing time. And this is equal to minus B times L times V. So effective voltage, or the magnitude of that, is simply E times L times V. And using the numbers given to us, that comes out to be 1.2 times the length. It's 10 centimeters, that's 0.10 meters, and V is 5.0 meters per second. So that's 1.2 into 0.1 into 5. That's 0.6 volts. volts. Coming to instance 3, in this case, the flux is not equal to 0. There is a magnetic field, there is an area of the loop. So this is not equal to 0. But what is equal to 0 is the rate at which the flux is changing. The rate at which flux is changing is indeed 0. And as far as the flux is changing, the induced voltage is 0, which implies the induced current will be 0. This implies I will be equal to 0. So we do not have to worry about the direction of the current because there is no current induced. So this was instance 3. Instance 4, the flux is now decided by how the area is changing, how the shaded area that I've shown just now is changing with time. Since it's moving out, that's actually decreasing. So flux is decreasing now. If the flux is decreasing, then the induced magnetic field will be along the direction of the original B. So if this is the loop that we have, induced magnetic field now will be into the pitch because original B was into the page. And for this, we need the current that will produce this magnetic field has to be going clockwise. So I is clockwise in the loop at instance 4. Effective voltage will have the same formula as we have in instance 2. So effective voltage will be still be LV, and the magnitude of that would be again 1.2 times length. L is still 10 centimeters. The velocity is 5 volts, which is again 0.60 volts. The only difference being that it is effectively equivalent to having a battery is attached in this loop in the opposite sense. So the polarity of the battery is flipped when it is going out of the magnetic field. Again, the system is trying to oppose whatever we try to do, trying to get out of the magnetic field, and it will actually pull it. So we will really feel a drag when we are trying to pull it out. But the system will try to pull it in. While we are pushing it in, it will try to push it outward. Finally, coming to instance 5, it's very similar to instance 1. We have the flux itself is equal to 0, and that doesn't imply that the rate of flux is actually 0. So the rate of change of flux is also 0 because that's a magnetic field everywhere, even in the as it is moving, it doesn't change. So that implies that the current will again be 0. With that, let me stop sharing and stop recording.